Spring by friction is necessary to make the disk in figure 7 forward roll in the direction indicated. A. Give the direction of frictional force at B and the sense of frictional torque before perfect rolling begins. B. What is the force of friction after perfect rolling begins? Now let us try to answer this question. Why friction is necessary to make the disk to roll in the direction indicated? If the disk is given an initial speed omega naught and is placed on the frictionless surface of the table, then the disk spins at the point where it is placed without any translatory motion. If there is friction between the disk and the table, this friction opposes the velocity of the point in contact with the surface. That means the point B. The velocity of the point B is Vb and Vb is acting towards left. Now, due to the sliding motion between the surface of the disk and the table, a friction force opposes this velocity. That means the friction force acts towards the right. This friction force acting towards right helps the disk to move towards right. If there is no friction, the disk will not roll in any direction, since an external force is necessary to move a body in any direction from rest. Now let's come to answer part A. Give the direction of friction force at B. We have already seen that the direction of the velocity of the point is towards left, that is Vb is towards left, and the friction force acts opposite to the velocity. That means F is towards right. So the answer is that F acts towards right. Now, due to the force of friction, the torque acting on the disk is given by tau equals the force of friction F into the distance of the point B from the center of the disk. That means F into R. This is the torque acting on the disk. This torque is in the anti-clockwise sense. So this is anti-clockwise. The frictional torque is anti-clockwise and the torque acts perpendicular to the plane of the picture outward. Now let's try to answer B part. What is the force of friction after perfect rolling begins? The condition for perfect rolling is that the velocity of the central mass of the disk is equal to R into omega, where omega is the angular speed at the instant. When this condition is satisfied, there will not be any sliding motion, only perfect rolling. So there will not be any sliding motion. And so the force of static friction reduces to 0. That means after perfect rolling begins, the force of static friction becomes F is equal to 0. Okay. A solid disc and a ring, both of radius 10 cm, are placed on a horizontal table simultaneously with the initial angular speed equal to 10 pi radians per second. Which of the two will start to roll earlier? The coefficient of kinetic friction is mu k equals 0.2. Let us write down the given quantities. It is given that the radius of the disc or the ring is R is equal to 10 centimeter. That is equal to 0.1 meter. Angular speed omega naught, the initial angular speed, equals 10 pi radians per second. Coefficient of kinetic friction mu k equals 0.2. Now, when the disc or the ring is placed on the table with the initial angular speed omega naught equals 10 pi radians per second, the force of friction calls into play, and as a result, the initial angular speed omega naught decreases and it may become another angular speed omega. Let V be the speed of the central mass of the disc or ring at the instant, then we can write V is equal to the acceleration A into T. where acceleration can be written as a Fk divided by m into t. So that's equal to Fk means the force of friction. Force of friction means mu k into mg divided by m into t, or it's equal to mu k into gt. If omega is the final angular speed when perfect rolling begins, then omega is given by omega naught minus alpha into t, that is equal to omega naught minus alpha means the torque tau divided by the moment of inertia I into t, that's equal to omega naught minus Fk into r is the torque divided by I into t, and this is equal to omega naught minus Fk means mu k into mg. So mu k into mg r into t divided by I. Now when perfect rolling begins, we can write down that the speed or the velocity of the central mass of the disk or ring v is given by r omega. So we can write omega as v by r, omega equals v by r. Therefore the relation can be written as v by r equals, therefore v divided by r equals omega naught minus mu k into mg rt divided by I, but v is equal to mu k into gt. Therefore this can be written as mu k into gt, that is the value of v divided by r, equals omega naught minus mu k mg r t divided by I. Let this be equation 1. Now for ring we can write the moment of inertia I as m r square. Therefore relation 1 can be written as mu k gt by r equals omega naught minus mu k mg r t divided by mr square, or that's equal to omega naught minus mu k gt by r. This can be written as mu k gt by r plus mu k gt by r equals omega naught, or we get 2 mu k gt by r equals omega naught, or we get the time t as omega naught into r divided by 2 mu k g equals omega naught r divided by 2 mu k g. This is the time taken by the ring to begin perfect rolling. That means tr equals omega r divided by 2 into mu k g. Let this be equation 2. Now for the disk we have I equals m r square by 2. Therefore relation 1 becomes mu k gt by r equals omega naught minus mu k mgr t divided by m r square by 2. This is equal to omega naught minus mu k g t 2 into mu k g t, omega naught minus 2 into mu k g t divided by r. So we get mu k gt by r plus 2 mu k gt by r equals omega naught, or we get 3 mu k gt by r equals omega naught, or we get the time t, we get the time t as omega naught into omega naught r divided by 3 mu k g. This is time for the disk. Therefore we get the time taken by the disk as Td equals omega naught r divided by 3 uk g. Let this be relation 3. Then from 2 and 3 we see that Td less than Tr. That is, the time taken by the disk to begin perfect rolling is less than the time taken by the ring to begin perfect rolling. Okay, now let us find the values of the time. 2 becomes Tr equals omega naught r divided by 2 mu kg, 2 mu kg omega naught r divided by 2 mu kg equals omega naught means 10 pi into r means 0.1 divided by 2 into 0.2 into 9.8. This when calculated we will get 0.80 seconds. Now 3 becomes Td equals omega naught r divided by 3 mu k g equals 10 pi into 0.1 divided by 3 into 0.2 into 9.8. This one calculated we get 0.53 seconds. Okay. A cylinder of mass 10 kg and radius 15 cm is rolling perfectly on a plane of inclination 30 degree. The coefficient of static friction mu s equals 0.25. A. How much is the force of friction acting on the cylinder? B. What is the work done against the friction during rolling? C. If the inclination theta of the plane is increased, at what value of theta does the cylinder begin to skid and not roll perfectly? Let's draw a diagram. In the diagram, the cylinder of radius r rolls down on an inclined plane. The height from which the cylinder rolls is h, and the distance from the cylinder to the bottom of the inclined plane is s. The weight mg of the cylinder acting in the downward direction can be resolved into two: mg cos theta perpendicular to the plane and mg sin theta parallel to the plane. The normal reaction n is equal and opposite to mg cos theta. It is in the upward direction. So the force of friction will be the coefficient of friction into n. Let's write down various quantities in the problem. First, mass of the body. Mass of the body equals 10 kilogram. Radius of the body capital R equals 15 centimeter equals 0.15 meter. Theta equals 30 degree. Coefficient of static friction mu s equals 0.25. Now let's do the first part, A part. How much is the force of friction acting on the cylinder? For that, let us consider the equation for translatory motion of the cylinder. The cylinder moves in the downward direction So the resultant force acting on the cylinder in the downward direction parallel to the inclined plane is given by mg sin theta minus the frictional force F acting parallel to the plane upward. This resultant force by Newton's second law is equal to the product of mass of the cylinder and the acceleration produced. This is the acceleration produced. Let this be equation 1. Now we can write down the expression for torque. Torque here equals the friction force F into the distance from the center of the cylinder. That means R. F into R is the torque. This is the torque. Therefore, we can write the expression for the angular acceleration. Angular acceleration alpha is equal to torque divided by moment of inertia I. So that's equal to Fr divided by I. But this acceleration alpha can be written as the linear acceleration divided by radius for perfect rolling. For perfect rolling we have Vcm, the speed of center of mass equals R into omega. Similarly, the acceleration produced for the center of mass Ac is equal to R into alpha. So we can write alpha as A by R, that's equal to Fr divided by I, or from this relation we get the linear acceleration A equals F R square divided by I. Now substituting this in equation 1, therefore equation 1 becomes mg sin theta minus F equals m into F R square divided by I. This relation gives that mg sin theta equals F plus F into mr square by I, or this may be written as F into 1 plus mr square divided by I. From this we get F as mg sin theta divided by 1 plus m r square divided by I. But for cylinder I is equal to m r square by 2, so this can be written as mg sin theta divided by 1 plus m r square divided by m r square by 2, or this is equal to mg sin theta divided by 3. Let this be equation 2. Now the value of F can be found from equation 2 as mg means 10 into 9.8 into sin theta means sin 30 divided by 3. This when simplified we get 16.33 newtons. This is the answer to the part A. This is the friction force acting on the cylinder. Now let us do the next part, that is the B part. What is the work done against the friction during rolling? So let's come to B part. What is the work done against friction during rolling? Here the work done against friction during rolling is W equals to 0, because the work done for rotation motion will be equal and will be of opposite sign to the work done in translative motion when the cylinder comes to the bottom. So the reason is that because work done for rotation motion is positive. Why it is positive? Here the torque is clockwise and the angular displacement is also clockwise. So both the torque and the angular displacement are the same direction, and hence the work done for rotation will be positive. and also work done for translation motion WTR equals negative. Why? The force of friction is in the upward direction parallel to the plane and the displacement S is in the downward direction parallel to the plane. So they are in opposite directions. Therefore, the work done by the force of friction for translative motion will be negative, and they will be of the same magnitude and of same magnitude. So that's the reason why the total work done is 0. Let us give a proof for this. Proof for total work done equals 0. Work done for rotation motion WR equals the magnitude torque into the magnitude of angular displacement. Here both are negative, so the directions of the torque and the angular displacement are the same, and hence we can find the work done during rotation motion as the product of the magnitude of both the torque and the displacement. So this is equal to the torque means F into R is the magnitude of the torque. So that into theta. F means we have seen that F is equal to mg sin theta divided by 3 for the cylinder, and this into R into theta means the displacement as divided by R. So total arc length is S. So S by R is the angular displacement theta. Now R gets cancelled. This is equal to mg sin theta into S divided by 3, or that's equal to WR equals mg sin theta by 3 into S means H by sin theta from figure, H by sin theta. So that's equal to mgh divided by 3. Now work done for translative motion for the same case is given by WTR equals here the force of friction F and the displacement S are in opposite directions. So work done will be negative. So it will be minus of the product of the modulus of the force and the displacement. That means minus F into S. That means minus F means here what is the value of F? F is mg sin theta divided by 3 for a cylinder, and S means H by sin theta. So here we get this as minus mgh divided by 3. Therefore total work done for rotation motion and translative motion against friction is given by W equals WR plus WTR equals WR means mg h by 3 and WTR means minus mg h by 3. This is equal to 0. Thus we see that the work done against the friction during rolling equals 0. Now let us do C part. If the inclination theta of the plane is increased, at what value of theta does the cylinder begin to skid and not roll perfectly? The cylinder begins to skid without rolling perfectly if the force of friction is equal to the maximum value of static friction. That means if the frictional force F is just equal to the maximum value of static friction Fs, or that's equal to mu s into n, but that's equal to mu s into n means what is n? N is equal to mg cos theta. Here F means mg sin theta divided by 3, and that's equal to mu s into mg cos theta. We can cancel mg from both sides and write sin theta as sin theta equals 3 mu s cos theta, or tan theta equals 3 mu s. This is equal to 3 into, what is the value of mu s? It is 0.25. 0.25. So that's equal to 0.75. Hence theta equals tan inverse of 0.75. This is found to be 36.87 degree, or this is approximately equal to 37 degree. Okay,